Okay, so let me start by thanking the organizers for this very nice and interesting conference and inviting me. And actually, the topic I'm going to mention today is about the so-called lattice quantization of gravity. And specifically, I will talk about the so-called dynamical triangulations, causal dynamical triangulations. And just in a minute, I will explain my topic, which is quantum gravity on a torus. Just let me very shortly start with the main motivation. So basically, I was kind of surprised that already Einstein in 1916, not just after the discovery of general relativity, mentioned that probably this theory will have to be modified by quantum laws. And I mean, still, quantum mechanics was not present at that moment. But I still have an impression that 100 years have passed, and we still don't have a really consistent theory of quantum gravity. So we have a number of various approaches. Sorry if I didn't mention one of your work. These are just examples. So there are many of them, and they are some kind of competing, or part of them have the same results, but there is still kind of less. Okay, so I will focus today on these lattice approaches, which so far were mentioned on this conference. So, okay, so as we all know, gravity, just formulated as conventional quantum field theory, is non-renormalizable in more than 2 dimensions, including physical 4. So, but as put forward by Steven Weinberg in late 70s, I guess, or early 80s, there is still possibility that a predictive and, let's say, correct theory of quantum gravity could be formulated nonperturbatively. And this kind of idea seems to be, I mean, maybe not still confirmed, but there is growing evidence that it might be possible that it might be so that the flow of renormalization group equations leads to some non-trivial ultraviolet points where the values of the coupling constants are not necessarily small. So this is why the perturbation expansion fails. However, it is still possible that this is well posed problem and everything is okay there. So somehow it leads to the idea that if we have this problem that we cannot compute something perturbatively, maybe we should use more or less the same thing as people are using in lattice QCD, in the limit of energies where perturbation calculus fails. And this leads to the idea of lattice methods. So let's say more or less try to apply the same methods as people in lattice QCD do to gravity. However, the problem seems to be much more difficult, especially because, as we know, gravity is about space-time geometry. So in order to encode these geometric degrees of freedom, we should use some kind of the dynamical lattice. What is also important, in order to be able to reach this ultraviolet point, so to have contact with continuum physics, we should have a system which has several phases and in which there are at least one second-order phase transition. And we also should, of course, be able to recover the infrared limit, which should be consistent with GR. So it seems that in order to have all these 3 conditions fulfilled, at least in our formulation, some notion of causality, which I will explain in a moment, is important, because without this, it somehow fails. Okay, which leads to my presentation. So first, I will very briefly discuss what is our approach, what is causal dynamical triangulations. Then I will discuss very briefly our previous results, which were mostly done for a topology of a sphere. I just will, in a moment, explain what I mean by this topology. And then our newest results, which are for the topology of a torus, which is the title of my presentation, quantum gravity on a torus. And then I will conclude. Okay, so causal dynamical triangulations is very basically a quantum gravity model which is based on the path integral quantization. So just to remind you very shortly, you all know that in classical mechanics, we just basically have one trajectory which is joining the initial and final, let's say, position or state, and which results from the earlier Lagrange equations of motion. But I mean, quantum theory is about let's say, probability, and quantum amplitude, which defines this probability, can be computed. This is what Feynman invented, using so-called path integral. So instead of having just one trajectory, you may suppose that you have infinitely many possible trajectories joining the initial and final state, and you should make a sum or kind of integral over all these trajectories. And then you are able, using some say, summing over these trajectories to compute transition amplitudes and things like that. Okay, and in practice, to be able to define what is meant by this path integral trajectory, one has to introduce some type of the discretization, regularization. So let's say in classical traditional quantum mechanics, one divides, let's say, the time into some small intervals, and one can define in each of this interval what is how this path integral is there, and then one has to sum over these integrals, and of course to get the continuum limit, one has to go with the interval size to 0 and the number of intervals to infinity. And we more or less want to repeat it for gravity. So of course gravity is about space-time geometry, and any geometry can be approximated with, let's say, arbitrary precision by a triangulation. So this is just a nice example of the triangulated Stanford rabbit. But of course, the smaller triangles you use, the better the approximation of the continuum or the continuum limit. And in this simple two-dimensional case, the local curvature is encountered in a number of triangles. Let's say we use equilateral triangles in a number of triangles which meet in a common vertex. And it can be generalized to more dimensions, specifically to 4 dimensions. And in this case, the curvature sits in the d minus 2-dimensional object. So if we use the generalization of triangles to 4 dimensions, these are called simplices, 4 simplices. And curvature is defined on how many these 4 simplices meet in a common triangle. Okay, so I mentioned that in our approach, some notion of causality is important. And by this causality, we mean that we somehow limit ourselves only to spacetime which are globally hyperbolic. And by Gerov theorem, it can be shown that such a spacetime can be topologically divided into space and time. Okay, so let's imagine we have some, we have some time. This is just the topological division. We have some time and some special degrees of freedom. And specifically, there is a long-standing discussion if in quantum gravity we should allow for topology changes or not. And I would say that half of the community says yes, we should sum over all possible topologies, and half of the community says not, we should limit ourselves somehow. And somehow, our approach is very simple. We just limit to just one chosen topology. Okay, so we just fix the topology of spatial sizes, which the first research was done for the topology of a free sphere. So geometry can be anything, but the topology is a free sphere. And then we have this time. Just in a minute, we impose time periodic boundary conditions because finally everything will be Euclidean. But whether this is an interval or whether we have this as one here doesn't matter for our solution. We check that it is just technical, that it's easier for us to impose this kind of a boundary condition. Okay, so we assume that the topology of each spatial slice is fixed. It cannot change from slice to slice. And we also fix the global space-time topology. And this is the, let's say, what we call causality. Okay. So, and our previous results were mainly for the spatial topologies of Torus, and right now we started to investigate a system with a spatial, it was for a spherical topology, and recently we started with a system with topology, spatial topology of a Torus. This is why quantum gravity on a Torus. Okay, so to be able to calculate this path integral, we just have to somehow define how this triangulation, define what we mean by this triangulation. And in the case of causal dynamical triangulations, we just build the space-time from just 2 types of the building blocks. So we call them 4 simplices, and each of these spatial slices is just built from equilateral tetrahedra, which are visualized here. And in order to connect, let's say, spatial slice in time t to spatial slice at next time, we need to extend this to 4-dimensional object, which is the so-called 4-1 simplex, because it has 4 vertices here and 1 vertex here. And to be able to glue all these simplices together such that we don't have holes, so also that not only in, let's say, that everywhere the topology is that of a of a, let's say, torus or a sphere. You also need the other type of a simplex, which is called the free-two simplex, which has a triangle in one time and a link in t plus or minus 1. And our approach is non-perturbative, so we have to sum over all possible realizations of such gluings with appropriate measure. Okay, so let me focus on a pure gravity model, so we don't at this stage add any matter fields to that. So just our action that we use is the normal Einstein-Hilbert action with Newton's constant and cosmological constant. And it can be shown that in case of these triangulated manifolds, these triangulations, or simplicial manifolds as we call them, this action takes a very simple form. So if you just put the triangulation to this action, you just get this expression. This is just a linear combination of some global numbers in the triangulation, like the total number of vertices, total number of four simplices, and total number of these simplices of type 4-1, which I mentioned. And we have three bare coupling constants, which are related to the Newton's constant, to the cosmological constant, and also another parameter which we introduce, which is an asymmetry in the length of links in time and spatial directions. Okay, so it has something to do with the speed of light, let's say. And then the path integral is defined in this way, that we have to sum over off triangulations obeying these topological conditions. We just sum the exponent of I times classical action. Of course, I mean, this kind of a theory can be solved analytically in 2 dimensions. However, in higher dimensions, we need to use computer simulations. So it's very complicated to do something with exponent to I times action. So what we do, we use a notion of the Vig rotation. So we go with this parameter, which was this asymmetric parameter, to negative values by continuing it in the lower half of the complex alpha plane. And then we end up with a Euclidean theory where we have some, let's say, partition function. We have the sum over geometries, and we have exponent of minus action. What is, in such an approach, what is equally important is not only the value of the action, but also the number of triangulations with the same value of the action. So some notion of the entropy, which enters there, let's say, which is equally important. So I won't go into details how we do it, how we measure it, but it can be done numerically using some Monte Carlo tools. So we have some more or less elaborated program which generates these triangulations with proper Boltzmann weights, so which are given by this probability distribution, and then we can use them to measure some observables. Okay, so let me first discuss the previous results which were done for this spherical choice of topology. So, you put it on the computer and you have to get some numbers, so you have to define some observable, and the easiest thing you can think of is the so-called spatial volume. So you have this foliation, and you can count how many tetrahedra is there in each of the, let's say, labels of time, and then it defines you the spatial volumes. Each tetrahedron has the same volume because they are equilateral, so just the volume is proportional to the number of tetrahedra which sits at time t. And just looking at how this thing behaves, which we call it volume profile, we have discovered 4 various phases of geometry or behavior of the system. Okay, what is on the axis? So this is one of the coupling constants. This is this one, which is more or less 1 over g. This is this delta, which is more or less this asymmetric parameter. And we also have the third coupling constant, but I won't go into details, but it has to be fine-tuned to some critical value, which is dependent on this k0 and delta. So effectively, we are left with just 2-dimensional, let's say, phase diagram. So everything can be defined on this plot. All right, so we identified 4 different phases of geometry. And if we look at this spatial volume observable, for example, in phase A, you see a sequence of uncorrelated maxima and minima. In phase B, everything is collapsed just to one slice. But the most interesting region are these phases C and CB here, when you see some extended region where the volume, where there is a blob of volume, so some, let's say, macroscopic universe forms. And let me just discuss this in more details. So let me first focus on this region of phase phase space, which we call phase C, and I just would like to argue that this has quite a good
properties which can be, attributed to the infrared limit of our approach. So first of all, we can mention what is the effective dimensionality. So even though we are using the building blocks which are topologically four-dimensional, it doesn't mean that the effective dimension, which is in this triangulation, has to be 4. And for example, if we try to compute it in phase A, it's closer to 2. In phase B, it's infinity. But right here in this region, it seems that what we get is very consistent with 4. So we can either use the notion of the so-called Causal dimension or scaling dimension. So what we basically do, maybe I won't go into much into details, but because I don't have much time, but we just can repeat same computer simulations for various system sizes, and then we rescale them by using some notion of dimensionality. And if we rescale it properly, we should get the overlap between different measurements. And it turns out that the best overlap is for dh equal 398 plus minus 01. So this is 4. We can also use a notion of the so-called spectral dimension, which is defined by some fictitious diffusion process in the triangulation. So you just start from some initial position, you just run your diffusion, and you look at the probability of return to the initial point. And this dimensionality can be defined by looking at this, how it behaves. It turns out that this kind of definition depends on this diffusion time. So if you are closer to the initial point or further from that, so somehow you can both track very short, let's say, length scales and these macroscopic length scales. And it turns out that for very short length scale it's closer to 2, but for these macroscopic scales is 4. And this is kind of important result, which Jakub will discuss in next talk. Okay, what is more, we can also measure, let's say, the average. But, individual triangulations doesn't matter. What matters really are averages or expectation values or correlators of some observables. Okay, so you can measure the average volume profile, and it seems that it fits very well to the de Sitter solution of the Einstein equations. Here we work in the Euclidean metric. So if you just put the maximally symmetric homogeneous and isotropic metric into Euclidean Einstein equations, then you get something which has the shape of cosine to the third, and this is exactly what we recover from our data, which suggests that if we just look at the spatial volume observable, just at this observable, so we just integrate, we have, let's say, full, of course, discretized, but full gravity there, but we are just focused on this observable and we integrate out over degrees of freedom. Maybe it can be described by some effective action, which is given by this kind of the, let's say, metric, which is put into Einstein-Hilbert action, which leads to the notion of the mini-superspace action, and this mini-superspace action, written in terms of this volume observable, is in this form. Okay, so it turns out that this kind of action, so this is our ansatz, and this ansatz can be confirmed also in numerical studies. It can be done by looking at fluctuations of the spatial volume observable around the average and the correlation between t and t prime. And actually, this kind of object can be measured in numerical simulations. And the inverse of this covariance matrix gives information about derivatives of second derivatives of the effective action. So we can really check that what we get is really this mini superspace action. So here, this is the discretized kinetic term plus potential, which really, it was quite difficult to show that it really fits to this v to 1/3, but it really does. And it's quite consistent. What is interesting, we have the reverse overall sign, but this is good because if you just naively plug this homogeneous and isotropic universe to the Einstein's equation, you get in Euclidean formulation, you get something which is negative and which is unbounded from below, okay? And we wouldn't like to have something which is unbounded from below. So this is somehow the effect of entropy, which is correcting this wrong sign. All right, now about more about the phase structure. I mentioned about this phase C, which we call the semiclassical phase, which has very good properties, and which can serve as an infrared limit of our approach. And there is also another phase that we discovered quite recently, like 3 or 4 years ago, which we are not aware of. It's there because actually just looking by this on the spatial volume observable was quite difficult to distinguish it. I mean, we maybe wasn't very careful. But it turns out that if we are in this region of the phase diagram, this dimension, this effective dimension breaks. It's no longer 4. It's closer to infinity. So it behaves a little bit like in phase B. However, we do observe some extended region of the universe. Also, the spectral dimension, I mean, these green results here were the results for this phase C, where it approaches 4. These red curves are in this new region, where it grows much above 4. And such a behavior, you see this kind of the behavior, suggests that there is high connectivity between the building blocks. So you can just imagine that you have some graph which is maximally connected, and this is more or less an illustration of this almost maximal connections between our building blocks, so our force impulses. And it turns out that when we investigated it very carefully, that really there are some volume clusters, four volume clusters which form in the system. There are linked, but some singular vertices which are present every second time layer. So in this phase C, this is this blue curve. There is no some special vertices, but in this phase CB, there is every second time layer you have some very high order vertex. All right, maybe. Let me skip this slide. It's not so important because I'm running. Okay. Now about phase transitions. Basically, how can we investigate the phase transitions? So first, we have to define some order parameter. This is just some parameter which is, let's say, small in one phase, or large, or constant in one phase and increasing in another phase. And we define some of these parameters. I won't go into details. This is their behavior in various phases. So this shows how these parameters behave on this line. This plot shows how these parameters behave on this line. So just to identify the point where the phase transition occurs, we can look at the so-called susceptibility, which is basically just the variance of the order parameter. And we are just checking numerically our system in search for susceptibility peaks. So when we have susceptibility peaks, it signals that there is a phase transition. And it turns out that really we could find such points where there are these susceptibility peaks. And if we tune our system very closely to this, let's say to this point, and we just look at the Monte Carlo history of the order parameter, it seems that it jumps between two metastable states, which is not good because such a behavior is typical for first order transitions, that you have two metastable states and some order parameters jump between the two. And it seems to be both the case for this transition and this transition. However, if we look at this thing more carefully, and if we investigate what happens when we increase our system size, it seems that these flips between these two metastable states disappear for higher and higher volumes, while here it is more and more pronounced. Which leads to the conclusion that this is really the first order transition. This is not good. We are interested in higher order transitions. But this one is really the second order. It can be also checked by looking at some scaling, how this transition point moves with lattice volume. And there is some exponent which is associated with that. And the value of exponent which is close to 1 signals this is the first order. But if it is far from 1, it should be second or higher order transition. And really this one is far from 1. And also this newly discovered phase transition between this semiclassical phase and this new phase is second order. Okay, let me turn to the final part, which are just the same results for the toroidal topology. Because the basic question is, I mean, we put this topology by hand, so we want to know how it depends on what we put by hand, okay? If we can recover more or less the same story, same structure. So the question is, so far it was for the sphere, and right now it will be for the torus. And the question is, first of all, about the existence of the semiclassical phase, if it is there, and about the phase structure. And still the open question is about the order of the phase transition, which it's still not measured. Okay, so let's start with this semiclassical phase. Okay, I still have 5 minutes. We again look at this volume, spatial volume observable, how it behaves. And it seems that for the toroidal coism is very different. Previously, you had this blob and this cosine to the third solution, but for the torus, it's flat. But if this kind of a solution for the spherical case was well explained by this ansatz, that this is the kind of mini superspace behavior. So if you plug the same ansatz for the torus, which is just the flat space time, you don't get this potential term, which was caused by the curvature, which was present in the spherical case, and it is not present in the toroidal case, which explains very well why we observe this flat volume profile. What is more, we can again measure this effective action. So somehow we can make this ansatz and check if it is consistent with our fluctuations matrix data. So we again compute this covariance matrix. There are various methods how to do it. It's maybe not so important, so I skip it. But the result is that for the toroidal case, we really do observe this mini superspace action plus some correction. And this correction we interpret as a kind of quantum correction. We don't have a good, theory behind that to explain why exactly this exponent is close to -3/2, but this is what we measure. Okay, now about the phase structure for the torus. So somehow the previous, what I just showed, shows that there exists this semiclassical notion of this semiclassical phase in the system, both for the spherical and toroidal case. So this is this one. The question is, are there other phases? Okay, so in this region of the phase space, there is something which looks exactly like phase A. In this region, there is this collapse phase. And there is also this phase where you see this jumping of the order of vertices between even and odd slices, exactly the same behavior as before. So we have all 4 phases. What is more, we can also measure the position of the phase transitions using more or less the same methods as we did before, as we used before. So we have these various order parameters. We look for susceptibility peaks. Here is the chart. So you see there is some. This is susceptibility plotted on this. This is in delta. Okay, so there is some line here. Okay. And we just check how it depends on delta. So you see this is this transition which occurs here, and this is this transition which occurs here. And we can compare the results between spherical case and toroidal case. Spherical case are these solid lines here, this line, and this line. And toroidal case are these points and also these lines which are some, and these are the error bands, these dashed lines. And it seems that it looks very similar. So the positions are almost the same. They are shifted a little bit, but why they are shifted? They could be shifted due to the finite size effects, which are different for the torus and for the sphere. And as I already mentioned, the exact position of the phase transition depends on the system size. So if there are different finite size effects, it might explain why these transitions are a little bit shifted. So to conclude, CDT seems to be a promising candidate for describing quantum gravity if this asymptotic safety scenario is really valid. And we have some kind of rich phase structure, including semiclassical phase, which is the infrared limit of the approach. And recently we have discovered this new phase CB with some interesting geometric features, which I didn't have much time to discuss here, but it's kind of interesting. And also this new phase transition is second order, and it seems that these results are quite universal. If you compare torus to the sphere, there is of course much more work to do and to include other topologies and repeat the same. Okay, so thank you very much. Oh, sorry. No, -1.
Can you show the torus?
Sorry, the what?
The extra term you get for the torus with this network we have.
Here, yeah.
So are you sure that this does not appear in the spherical case, or is it just more?
No, we are not sure because this is subdominant. The problem with the sphere was that we have this potential which was V to 1/3, okay? So which was completely so this term, if it is there, is completely hidden in the data. So we just somehow using the sphere we couldn't measure it, even if it is there. And this is the virtue of the torus, that we can measure such terms.
Well, that looks a little bit like the terms in the affine quantization. There's a repulsive potential in it.
Yeah, so maybe, I would be very happy to find some link with some other approaches which could explain why it is there. I'm not aware of such, this is the numerical value, so I'm not exactly sure that it is 3/2, but
it's also
yeah.
positive,
Yeah.
seems like.
So yeah, if there is such link, we are very interested.
Back to the next lecture. Thank you very much again. Okay, we thank the speaker again.